and welcome to this video presentation of the paper Text the Stealthy Adversarial Face Masks being published at TMLR. My name is Ben Lewis, one of the authors of this paper, and let's begin. So this paper is proposing a new way to generate adversarial face masks for face recognition systems. So there exists these machine learning AI systems that, given an image of someone's face, will identify who that person is. And people therefore made these face masks so that when a specific attacker wears the face mask, there's unintended behavior in this system. So they're adversarial face masks. So for the purposes of this presentation, we mean that the attacker is misclassified. So it's classified as anyone except themselves. So there is other objectives for this, but to keep it simple, that's what we're going to focus on here. Now, previous workers have done a good job at doing this. They're very effective, and we have some images from their papers here. However, the problem with previous work is that they're not inconspicuous. So if a human looked at these face masks, they might think something a bit dodgy is going on here, something's not right here. So what we try to do in this work is generate face masks that look stealthier, so they look closer to a style reference image that we've given our style reference text. So how we plan to do that is by leveraging a new piece of technology called diffusion models. And here we have some images from a famous work called Diffusion Models Beat GANs of Image Synthesis, where you can see on the left here, the images generated by these diffusion models are significantly more diverse and have more life to them per se than the ones on the right generated by the GANs, where they kind of all look very similar structurally wise. And we plan to leverage this new generative capability to generate new adversarial face masks that manage to keep this balance, this trade-off between stealthiness and adversarial efficacy. So we proposed this new attack called diffusion attacks for face recognition called DAFR. And we have this diagram here that kind of outlines how this works from a high level. So given some images of the attacker, so we have some images of one of our lovely co-authors here, and we have a style, so here blue flowers in space. It will manipulate the diffusion process, so how the diffusion models work, they use its diffusion process to turn noise into an image, the content you want. And here, midway through the diffusion process, or how deep you decide to set it based on high parameters, the attack will start basically placing the kind of generated image so far onto the face, onto the kind of face mask on the person, and use that information in the adversarial update phase to update the original texture so that it is more adversarial. So it's also going to, our plan here is that it's going to be adversarial and be stealthy, so it'll be the original style. And we're applying this in the latent space, which is how these diffusion models generate. So to give you some kind of reference to how DAFR looks, here are the styles we want here, kind of purple shapes on the left, blue flowers on the right. And for different facial recognition systems, we get different results. So here you can see DAFR does a very good job at keeping to the style and being adversarial. I think these face masks look very inconspicuous. I think they look very good. But for other networks, we found there's different trade-offs between how much stealthiness you want and how much adversarial efficacy you want. And this trade-off can be controlled by the attacker, and this is a benefit to DAFR. That is, this flexibility is part of the system and can be controlled through high parameters, while still being stealthy in all kinds of cases. Another part of this work was proposing a new benchmark to evaluate these adversarial accessories so that they are both robust to physical conditions. So if you actually made one of these masks in the real world and wore them, would it be effective still? And so you can evaluate its stealthiness. So how this benchmark works is that a texture will be generated on some given images of the attackers, and then will be applied on a test set where different transformations are performed to kind of simulate being in a different environment. So one of the transformation we do is random brightness, so we kind of jitter the brightness levels of the image to see if the face mask is still effective. Another one is match lighting, where we change the lighting on the face mask itself to match the rest of the image. And in general, when people do this benchmark, they can add any transformations they want, which makes it very modular, very flexible, and we believe is a good way to evaluate kind of robustness in this way. Another part of the benchmark is evaluating the stealthiness. So for this, we take a recent measure proposed um, called clip mean measure discrepancy, or CMMD, which is to measure how effective an image generator is, sorry, at generating images that align with a given distribution. So we're kind of treating our attack DAFR as a generator, which is trying to generate new images that align with that style. So the lower this discrepancy is between the two distributions, the stealthier the masks are. So if you look at these numbers here from the paper, in the red circles here, you can see that DAFR always has lower CMMD than the other previous works, and that means it is stealthier, it is closer to the original reference style, and for these networks, does not sacrifice that much adversarial efficacy, if anything at all. So this is for these networks, we found DAFR to be incredibly effective and achieve its goals. For other networks, we found that DAFR is able to produce stealthy face masks. As you can see here, the CMMD numbers are still lower, but there's a trade-off here based on the high parameters, which the attacker can control. So this allows DAFR to have this flexibility, which is very desirable for these attacks, as the attacker can choose what they want from that trade-off through just the high parameters, which is desirable. We also test this attack in the physical world, in the real world. So what we did here is we actually printed out some of the masks generated by several of these attacks, not just DAFR, and tried them in different locations and seen how they perform when we actually upload them to the facial recognition system. And we found that our results are consistent with the digital world, and that DAFR is still an effective attack. Thank you for listening to our presentation. If you want to find out more details, then please read our paper and the supplementary materials. If you have any more questions, then please reach out to us and ask us.